Hello and what's up to you all grade 10 Mindsetters. My name is Abram and you have joined us to learn more and learn extra on a physical science show. I hope you had a great day at school and I'd like to hear how was your physical science class today. Otherwise, we're here to learn more with Tracy. How are you, Tracy?
I'm very well, thanks, Abram. How are you?
I'm feeling good about this show and this lesson.
Absolutely. So my mindset is we've got so much in store for you, and so I really want you to pay lots of close attention. Today we're going to be looking at the periodic table, and specifically on the periodic table, we're going to discuss the arrangement of the elements in the periodic table. So why are they arranged the way they are? And then we're going to practice working with electron configurations. Now I know electron arrangement, electron configurations can be tricky, so watch out for those. We want to practice lots of those. And then we're going to look at trends. And trends in the periodic table, we might be thinking electronegativity or atomic radius or those type of trends. So we've got lots to cover today.
Awesome, and there's lots to tell you. Also, firstly, join us on facebook.com/learnextra. Like the page, share the page with all your friends, your classmates, even your teachers. Tell them about Mindset, and we can also help them. Otherwise, follow us on Twitter @learnextra. And lastly, download your notes at learn.mindset.co.za. Good news are, if you download your notes right now and do the test yourself questions, submit them via the link that is posted on Facebook, you stand a chance of winning an awesome airtime voucher, proudly sponsored by Vodacom, worth 110 Rand. And speaking of which, Tracy, we have a winner.
Have we got a winner?
Yes.
Awesome.
Her name is Progress Mzimba. Congratulations to you, Progress Mzimba. I hope you're shaking Mzimba wako there at home as we say congratulations to you. You've won yourself an airtime voucher, proudly sponsored by Vodacom. And you could be next, Mindsetter. So stay tuned, answer those test yourself questions, and you could be the winner tomorrow. But otherwise, we have the challenge question also for today. Tracy's going to tell us more about it.
Thank you. So mindset is we want you to be thinking. Science is all about applying your knowledge. So you've got to know the theory, but you've got to be able to apply. And so I've brought a challenge question for you today that I want you to answer. And here it is. It's also on Facebook. You need to go and answer it on Facebook and post your answer. But think about it. Sue argues that the radius of an atom increases with increasing atomic number. So her comment is that as the atomic number goes up, the radius goes up. Well, consider her statement. Do you agree with her or not? So you can say, yes, she's true, or no, she's false, or whatever. Provide a full answer, and my hint there is full. It needs to be a very well thought out answer. Just going back to this, radius, we're talking here size of the atom. Why? Well, because when I speak about atomic radius, I mean from the center to the edge. That's not quite the center, but you got the idea. From the center of the atom to the outside, that would be the radius. So go and think through that question, think through your answer, and make sure it's a full answer. Abram, do you want to tell us where they need to post their answer for the challenge question?
Yes, of course. The answers should be posted on the link, on the posted question, which is on Facebook. So you look at the picture which has the challenge question, and then put on your answer on that link, because later on we'll be giving you the answer on that very same link.
Excellent. So mindset is, let's get straight into the periodic table. We've got lots to cover, and I want you to make sure, because this periodic table is what you're going to refer to all the time in chemistry, specifically as you think through what different elements you've got. And it's very, very useful if you can understand the trends and understand the positioning of the elements and why they're positioned as they are. So, a few words in terms of terminology. When I speak about vertical columns, that's going up and down, those are called the groups. If I speak about horizontal rows going across, that's going to be what we would speak about as periods. And I want you to note that elements are arranged in increasing atomic number. Now, what is the atomic number? Remember, that is the number of protons in the nucleus. So I want to come across to the periodic table that I've got on the screen and just highlight a few things for you here. When I speak about a group, I'm meaning a vertical column. So that's going to be a group. And I would call that group 1. A period would be going across. Whee, all the way across. I just happen to get the key in there as well. Okay, that is going to be a period. This one in the center here is just our legend or our key. So it's not actually part of it. But got the idea. Going across is the periods. Going up and down are the groups. Then one other thing I want us to note is this number, and in this periodic table it's given at the top, the atomic number. So notice it's going 1 for hydrogen, 2 for helium, 3 for lithium, 4 for beryllium, 5 for boron, 6 for carbon, and so we can continue. That is saying that that's the number of protons in atoms of that element, okay? Which means that if you've got a different number of protons, you've now suddenly got a different element, okay? Very important, number of protons, atomic number. And you can notice that that is increasing with increasing atomic number, okay? Number of protons, that's how it's arranged. So we've covered our first 3 comments there. Then I want us to consider electron configurations. Consider the arrangement of the periodic table. And I want to go across here and just pick up a few of these for you. So I'm going to start with hydrogen at the top. It's got 1 proton, so let's write it there. Hydrogen's electron configuration, it would be 1s1. Why? Because it's in the first spherical orbital with 1 electron. Then the next one, helium, it's got 2, so helium over here would be 1s2. It's got 2 protons, so 2 electrons, they would fill up the s orbitals. Then let's jump across to lithium. Lithium has 3 protons, check it with me, lithium, 3 protons, so therefore it's going to have 3 electrons. So 1s2, because we'd filled up 2, now we've got to go 2s1. And do you notice a bit of a trend that I've got going here? This is, and I specifically want you to catch this, has got 1 for this group, 1 electron in the s orbital. The next one down has got 1 electron in the second s orbital. Directly below that, if we go across, you can go and fill in sodium. It's 11 protons, 11 electrons. It will fill up the third orbital, the third energy level with S3s1. And this whole block is called the S block. Why would it be called the S block? Well, specifically because it's going to always have its outermost valence electrons in the s orbitals. So the periodic table, this amazing table, has been arranged with this electron configuration where the whole block here is filling up s orbitals. The first group will be the first column, would fill up S1 always. The second one would fill up S2. Of course, except helium, which gets shifted across because it's a noble gas. Then the transition elements, we notice there, are filling up the d blocks. Now, we haven't done d orbitals, but as you can continue, you fill up more orbitals, and those would be the d orbitals. Then next we come across to the p orbitals. And I'm going to pick boron across here, boron. Go and find it quickly. It's got 5 protons, so therefore 5 electrons. It would be 1s. Sorry, let's just undo that. It's going to have 1s2, 2s2, 2p, well, it's got 4 already. 2 plus 2 is 4 plus another 1 will give me boron with its 5 electrons. Notice that now suddenly we're in the first p orbital. So now we start what we're calling the p block. And this is very, very useful because immediately I can look at it and say, hold on, where's that going to have to be? It's going to have to be in the p block, so across on the right-hand side of the periodic table. Or it's in an S block, it's going to have to be group 1 or group 2, okay, depending on obviously how many are fitting in there. Then there's something else that I want you to pick up. The period gives the last energy level that is filled. So have a look at this. This started with number 1 and ended with number 1. And it's in the first period going across. This one ended with number 2 and it fits into the second row or the second period. And so that's the next little thought to have there. The period gives the last energy level that is filled. And so it becomes actually quite easy to do those electron configurations that some of you may say you were struggling with. Work through them, recognize the first two groups would always fill the s orbitals, and then on the far side p orbitals. The group number, this is another valuable one, will always tell you the number of valence electrons. So have a look. Group 1 will have 1 valence electron. But hold on here, what about this one? Well, it's got 1 there, but 2 here. And this whole section would be the second energy level, which is, for boron, the final or last energy level, outermost energy level. And what does it have? It's got 2 plus 3, which is giving us the third group, or group 13. Now, I want to note that it is called group 13. Why is it called group 13? Well, because what we're ending with here is, what about these other 10, the transition metals? And those transition elements, they said, but surely you can't just ignore those. So some periodic tables you might find end with, or begin those with group 3. Some of them refer to it as group 13. But if it's group 13, well then you just need to consider that you've got to take away the 10 from those transition elements, so that you can recognize the valence electrons. It's going to be 3 fitting into group 13 or group 3, depending on which way you're thinking about it. The more modern way is to include those transition elements. If I flip over the page, we need to talk through some trends. Now, when we speak about trends in the periodic table, we're wanting to pick up what kind of relationships could we identify in terms of elements following after one another, in terms of how they possibly would react or behave. Atomic radius. When I speak about atomic radius, and I mentioned it at the start, it's the measure of the size of an atom. It's from, if that's my little atom, from the center to the outside would be the atomic radius. And that would flow from what you would know from maths. Ionization energy is something new. This is one that you probably haven't come across before, but it's an incredibly important one. Ionization energy, they tell you what it is, even in the word. It's an energy value. It's how much energy do we need to put in to take away 1 electron. Which in a sense, if you've taken away an electron from a neutral atom, is going to mean that it's going to have formed an ion, because it's now no longer got the same number of protons as electrons, because you took an electron away. So the ionization energy is the energy needed to take an electron away and cause that thing to now become an ion. Okay? So the energy needed to remove 1 electron from an atom in the gaseous phase. We could also speak about the second ionization energy, which would be the energy needed to take a second electron away, or the third ionization energy, the energy needed to take a third electron away. The focus here is it's an energy of how much energy do we need to put in to pull an electron away, to take an electron away from that atom. and cause it now to become an ion. And remember, an ion is a charged particle. Okay? Electronegativity. That's another big trend that we're going to talk about, but we have to define it first. It is the tendency of atoms to attract electrons towards themselves. And I would want to add there, it's the ability of an atom to attract a shared pair of electrons. Okay, so we'll come back to that one. There are a number of trends. And as you go across the table, as in along the periods, along the rows, there will be certain trends. What you need to notice is that electronegativity increases as you go across, specifically highest in the halogens. Why? Well, because within that group, also within that the energy level, because it's, remember we said now the second period is going to only have 2 energy levels. The third period will all have 3 energy levels. Within that energy level, as you go further along, there are now more protons inside the nucleus, and so they're attracting and attracting more to those outer electrons. Ionization energy would also be very high towards the right-hand side, and atomic radius would be high on the left-hand side. So these are kind of trends. Think through them and be able to explain each of them. Then if we look down the columns or within a group, so group 1, and let's talk all about group 1, there will be certain trends as well. I want to highlight to you atomic radius. It's one we'll come across quite a lot. Atomic radius means that the size of the atom is either getting bigger or getting smaller. And as you go down, it's high at the bottom, which means that the size of the atom is getting bigger. Why? Well, because each time, remember, we go down, we've got another energy level we're taking into account. So from 1 to 2, now you've got a second energy level. Now 3, you've got a third energy level. 4, you've got another energy level, which means that ionization energy will be less at the bottom because that electron is far away from the central nucleus, which means it's not going to be attracted as or pulled as much to the central nucleus. So it's not going to be attracted, which means it's easy to pull an electron away. You won't require as much energy to remove that valence electron to form an ion. So think through these trends. It's very, very helpful to be able to explain them, and hopefully we'll pick up on some of them in our questions today. So make sure that you go and do some test yourself questions, do the challenge question. There's lots on the go for you, and we'll come back and tackle some more questions. Abram.
Thank you so much, Tracy. And it's only 4 questions for the test yourself questions. We've added a bit of a twist just to help your mindsetters. On the post that says competition details, we've also posted the questions. So you can just copy the questions, write your answers down, and then send them back to us. Otherwise, we'll see you after the break. Welcome back, Mindsetters. If you just joined us now, you're a bit late, but you can still catch up. There's a lot to be done. Download your notes at land.mindset.co.za and learn more with us. The challenge question is posted on our wall on facebook.com/learnextra. I like the questions that are already coming. So if you're struggling and have some questions, send them through. We'll help you, me and Tracy, later on. Otherwise, I love this comment, Tracy, and I thought I should read it out for you. Tepiso says, wow, guys, I got 90% in my physics test, and it's all thanks to you. Keep doing what you guys are doing. You rock. You rock too, Tepiso.
Awesome.
Well done.
Well done. Well done. Lots of hard work your side, I'm sure, as well. Thanks so much, guys. Really, really important that you challenge yourself, that you ask questions, that you answer questions, and you think and apply the knowledge that you learn. Very, very important. Well done. Congratulations. That's awesome. Let's go across to improving your skills, because these are the kind of questions that maybe you could come across and see. So consider the following electron configurations and answer the questions that follow using the letters A to E where appropriate. So we've got a list. And this list is giving us a whole bunch of electron configurations for different atoms. And that's, I think, what the question originally said. It would specifically have to be for atoms. And I think I need to add that in here, Because if it wasn't an atom, then if it was an ion, a charged particle, then it could have a different number of electrons. And so we wouldn't necessarily be able to answer the questions. But if these are all atoms, they're all neutral particles, they all have the same number of protons as electrons, that would definitely be something we could do. So here's our list, and when we answer the questions, I'm going to answer A, B, C, D, etc. Okay? So, and I've thrown this in here because I know students don't often like these electron configurations. They can be tricky, but hopefully, if you've thought through what we just spoke about in terms of the periodic table and the way it's arranged, we should be able to answer quite a few of these. So, the first question says, identify a halogen. Now, what is a halogen? Halogen is something that is in group 17 or group 7, depending on which way you're considering it. It would have, therefore, 7 valence electrons. Which means what? Because 17, remember we said 17 minus the 10, the transition elements. So group 7 or group 17 will have 7 valence electrons. Now I need to go across and do my counting. So I'm going to come along here and pick how many valence electrons in the third orbital there. It's going to have 6 valence electrons. How many there? Well, this one will only have 1 valence electron. What about here? This is going to have 3s2, 3p5. So the 2 plus the 5 will be 7 valence electrons. And I found my answer. It's going to be option C. Identify a halogen, option C. Have a look at the rest of them. Only 2, 6, 1. So no, none of the others fit. But I want you to pick up here that we were counting the whole of the last energy level, which means everything in the third energy level for the first one. It's not just 4, but rather 4 plus the 2, which is giving us the total of 6 in that valence outermost energy level. So watch out for those. Great, first one done. I'm just going to clear these away so that we can make sure we've got space to answer these. Which element is found in the second period and the third group? Okay, so second period is going to mean, how do the periods link up with these electron configurations? Second period, or the second row, is going to mean that it's in the second energy level. So I need to write that down. That's going to mean second energy level, because the period links to the filled outermost energy level, which is, or the outermost energy level, which is the same as the period. And then they tell us the third group. Okay, or maybe the question should have been rephrased, the 13th group. Well, have a look at it. We've got to come across. We said second energy level. So A is out, because it's in 3. B is out, it's in 3. C is out, it's in 3. Do you follow how we're doing this? We're looking for where does it end in the second energy level. D is an option. E is an option. F is an option. But we've only just done the first part, the second period. What about the third group? Well, the third group means that it's going to have 3 valence electrons, because it would be 1, 2, transition elements, 3. Okay? So, or we could have, and I'm going to write in here, or group 13, depending on how the question was phrased. Now I need to come across. Where would D fit in? D would fit in 1s2, 2s2, which means, and I'm going to jump across here, it would be it would fit in 1s, 1s2, 1s, oh sorry, 2s1, etc. Let's keep going. It would be the third group. It would have to be fitting in with 3 valence electrons. So notice here, that's going to have 3 valence electrons. This one is going to have 8 valence electrons. This one only has 2 valence electrons. So my option must be F because it fits both criteria. It's in the second period, which means the second energy level, and it's in the third group because it's got those 3 valence electrons. So my option there is F. Identify an alkali earth metal. Now, alkali earth metals, you need to know the names of a few of these groups. So group 1 is the alkali metals. Group 2 are the alkali earth metals. So here we have, this must be in group 2, which means, therefore, that it must have 2 valence electrons or outermost electrons. We don't know the period that it's in, but we do know that it can only have 2 valence electrons. And I worked some of these ones out earlier, so I can just take those away and head back here. This was 6 valence electrons, that was 1 valence electron, 7 valence electrons. The only one that fits, there it is, it's got 2 valence electrons. I'm going to just circle that slightly more better. There you are, 2 valence electrons. So my next option must be D. Do you recognize that although my final answer is actually only 1 letter, I still need to do a bit of thinking. And that thinking, don't just throw letters around. It really is about thinking and reasoning it through. So make sure that you do that. Which will form positive ions when they bond? Now, in order for something to form a positive ion, what's it going to have to do? It will have to give away its valence or outermost electrons. Okay? Which ones will do that? Well, they're going to form positive ions. Which ones will form positive ions? When they only have 1 or 2 to give away. So, options here are things with only a few valence electrons. We said, and I'm going to write these in here again, this was 6 valence electrons. 2 plus 4 is the 6. This one only had 1 valence electron. Now, going back to these, it's helpful to recognize when things bond that they're going to want to have a filled outer energy level. So, which is the shortest route to get a filled outer energy level? When those that only have 1 valence electron or 2 valence electrons, they're going to have to gain, for 1, an extra 7 valence electrons to get a filled outer energy level. Or for 2, an extra 6 valence electrons to get to that filled outer energy level of 8. Instead, if they give away, then they can go revert down to the lower energy level, and then that is filled. Okay, so it's going to be stable. It's critical to note here, the ones that are going to form positive ions must give away valence electrons, and those would be metals, okay, that would be willing to give away. They will have very few valence electrons themselves. So then saying instead of gaining an extra however many, they can rather just give those away. So which are the ones with the lowest number of valence electrons? B, definitely. D, definitely, only has got 2. And F, definitely. So we've got 3 options here. B, D, and F. All will give away, for B it was 1, it would give away that one valence electron. For D, it was only had 2, so very willing to give those away. Although, hold on, possibly not, because 2, if I look at it, so D, if I look at it, is actually helium. And I'm going to jump, no, it's not. It would be, jump across. For a second, I thought that was helium. It's not. 1s1, 1s2, 2s1, 2s2. It's beryllium, and it's definitely going to form a positive ion. If there it was, that's probably boron, and that's going to only have 3 valence electrons, which would give it away. Let's keep going. Comparing elements B and F, which will have the lowest first ionization energy? When I speak about ionization energy, remember we're saying it's the energy needed to remove an electron, to take an electron away, right? So, how would that relate? Well, the focus here is how much energy, how easy or hard is it going to be to take an electron away from an atom? If the atom is small, so let me give myself some space, and I'm going to, at the bottom of the page here, write up lithium. And then directly below it, oh sorry, we don't need a calculator. Directly below it, I'm going to write sodium. Lithium has its 2 energy levels. Sodium has its 1, 2, 3 energy levels. And I'm exaggerating these. That was sodium. Let me redraw the second part, because I haven't drawn it particularly well. Let's redraw that quickly. It's going to have its sodium with its 1, 2, 3 energy levels. That's slightly better. To identify here that from the center to the outside, and from the center to the outside, it's getting bigger. Why is it getting bigger? Because it's now got an extra energy level. What happens if I'm trying to remove that electron that is sitting there? Which one would be easier to take away? Well, the central nucleus, remember, that's the positive, guys. The protons are sitting there. This one's got 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The nucleus is much further away, or that electron is much further away from the nucleus, which is going to mean that it's got a much weaker pull or weaker attraction. So, comparing those two, which one would be the easiest route to take away an electron? It's going to be for sodium, because the valence electron is much further away from the central nucleus. And that's going to help us answer this question. Comparing B and F, which will have the lowest first ionization energy? The lowest energy, well, we're now looking specifically at B and at F. They've got different numbers of electrons, but think this through. This is getting to energy level 3, which means the third energy level. In comparison, F is only in the second energy level, which means this electron is going to be further away. So B is my answer. Why? Well, because it has the most energy. Whoopsie. Trying to get fast with my handwriting. It doesn't work. Energy levels. And so your focus here is that the valence electron will be further away from the nucleus, which means that less energy is required to take away that one valence electron. Write down the chemical name for symbol A. So you could do this for all of them, but they're specifically asking for symbol A. I want us to go through this. The quickest way to do it is to jump right to the end and say, okay, where am I looking? I'm looking in group 6, and I'm looking in period 3. So let's have a look at that. I want to look in group 6 or group 16, depending on the periodic table that you're looking at, group 6 or group 16. And I said the 3rd period. So the 3rd row, going back to it, recognize why. We said it's got 6 valence electrons and it's filling the 3rd energy level. So I need to go across here to my periodic table and say, okay, let's find group 16 and let's look for the 3rd energy level. So going 1, 2, 3. It's going to be sulfur. Perfect. We can fill in sulfur, and as the whole name, not just the symbol, which will have the electron configuration simplified to neon 3s1. Well, first I want us to write a neon's electron configuration. There it is. It's got 10 electrons. So I'm jumping across, and I'm going to write, well, it's 1s, 2, 2s, 2, 2p, 6. 2 plus 2 is 4, plus 6 is 10. That's neon's electron configuration. What about that extra bit? Well, that extra bit is coming. So that whole thing is standing for neon, Ne. And then it's got the extra bit. So let's have a look at it. It would be, all filling in? No. B, look here, 1s2, 2s2, 2p6. That's exactly what we had for neon, except we have to add the extra bit, 3s1, which is what you've got there. So my final answer here would therefore be B has the same electron configuration there. We've got no more time for questions just yet, but what I'm going to do when I come back, I've got one more improve your skills question, and I know we need to tackle that challenge question. So I think let's take a short break, and when we come back, we're going to handle some more questions. Abraham.
Thank you so much, Tracy. In the meantime, send your questions on facebook.com/LearnExtra. We'll see you after this break. Welcome back, Mindsetters. Now it's always inspiring hearing you guys talking to us and sharing some of your wonderful stories. And there's another sweet comment, Tracy. This one is from Mishek Mavungu saying, "Hola, my top Mindsetters. I wrote a test out of 70 and I got 58, and thanks to you." Well done, Mishek.
Well done.
And you can still get that 70 out of 70. So keep learning with us and try again.
Awesome. Awesome. Well done. Congratulations. Any improvement is what we want to see. So well done. Keep going and be encouraged, because sciences can be really challenging. So really important that you're thinking about these things and challenging yourself even more. Talking about challenges, I've got the challenge question up on the board, and I want to think this through with you, because it's actually a complicated question. Sue argues that the radius of an atom, remember we said radius was the size from the center to the edge, okay, increases with increasing atomic number. Consider her statement. Do you agree with her or not? Provide a full reason for your answer. And I highlighted the word full to you because actually there are two parts to this answer. In one sense it's true, and in another sense it's false. And it's important that you identify both for your full explanation. So let's pick up where she's wrong and where it's false. So we'll pick up here. Why would we say that this is false? Well, as you're going along, what you're going to find is that as you go, and I'm literally going to just sketch a quick periodic table here. Okay, something like that. As you're going across the periodic table. Yes, you are actually increasing in atomic number. Why? Well, as you go across, have a look at those numbers. It's going 3, 4, 5, 6, 7, 8. Atomic number is increasing. But what do we notice about the atomic radius? Actually, as it goes across, the atomic radius decreases, which is in complete contradiction of her statement. She said that the radius increases with increasing atomic number. But as you go across, the radius decreases. It's high over this side and low down there. Well, across there, I should say. Why is that? Well, the reason for that is because along a period, remember I said the same number of energy levels. Period 2 will have 2 energy levels. As you go along, the radius is going to get slightly smaller. Why? Because that outer energy level, that level 2, is going to be pulled closer because of the stronger pull of the more protons inside the nucleus at that energy level, right? But, so we must say false. And our reasoning there, and I want us to jot it down, is that it would atomic radius decreases, important keyword, along a period. Or maybe you want to say across a period. As you're going across, the atomic radius is getting smaller and smaller. Okay? So definitely we've got to disagree with her. But partly she is true. And I'm going to write here partly. Why? Because I don't want you to get contradiction. Remember, that's why I say we've got to have a full answer. As you go down a group, so as you go down a group, what do you notice? So going down on that periodic table, and I'm going to sketch once again a quick periodic table. Okay, I just want you to see the general picture. As you go down within, say, group 2, okay, or group 1, the number of energy levels is increasing at each time you go down the group. And I sketched this for you a few moments ago when we answered this question. Lithium had 2 energy levels. Directly below it, we're now going to 3 energy levels. Below that, it would be 4 energy levels, and so it would continue. So as you go down the group, as you go down the group, sorry, let's go back to this one. We would say atomic radius does increase. And you would notice that the atomic number also increases. Lithium was 3, sodium was 11. Going down, potassium I think is 19. Check it. Potassium, there it is, 19. And so yes, atomic number is increasing and atomic radius is increasing as you go down the group. Atomic radius does increase and atomic number also increases. Now it's critical to identify that these 2 parts of the same of your answer have to both be there, because they asked us to provide a full reason. And so yes, I partly agree with her. As you go down a group, the atomic number increases and the atomic radius increases, so that's true. But as you go across a period, the atomic number increases, but the atomic radius gets smaller and smaller. So watch out and make sure you would answer these questions fully. Okay, I want us to spend a moment and go back and answer one or two more of these, improve your skills. Explain what is meant by the term electronegativity. Electronegativity is a new word, a new phrase. It refers to the pull of an atom on a shared pair of electrons. So I'm going to do a quick Lewis diagram here of hydrogen chloride. Notice I'm doing little crosses for the 7 valence electrons for chlorine and one little dot for this one for hydrogen. Okay, I'm just doing them slightly closer together. Hydrogen with its 1 and chlorine had its 7. Now I want you to notice that they've come along and they're making a shared pair there. They're sharing that pair of electrons so that they both have a filled outer energy level. Electronegativity is the ability of an atom to attract a shared pair of electrons. So notice I've given you an example there, and it's kind of like a bit of a tug of war. They're fighting over who gets bigger share of this pair of electrons. And we have electronegativity given to us on the periodic table. There it is here. It's given to you as a number on the periodic table. And you can go and look. Hydrogen has 2.1, electronegativity of 2.1. Chlorine has an electronegativity of 3. And you can go read off those numbers and tell me who wins this battle. Well, not quite wins, but who's kind of getting the bigger share of the pair of electrons. In this case, chlorine is. So the electrons are going to be tugged slightly closer to the chlorine side as opposed to the hydrogen side. But remember, it's a tug of war. They're both getting some, but not an equal share. Identify the trend. We spoke about this trend earlier. As one moves across the period, we would say there, electronegativity increases as you go across a period. So going across a row, the electronegativity increases. And that's because, once again, there are more protons inside the nucleus and the bigger tug of those electrons are being pulled closer. And so, again, a shared pair of electrons is going to be pulled slightly tighter as you go across. But look at the periodic table, read through it, and see what you can find. Now, I'm sure that there are 1 or 2 questions from you. I've seen a question about the S block and the P block. Those are names we can give to these different areas in the periodic table because of where the final valence electron is going to sit. And if you want to go back, I want to suggest to you that you actually go out and draw out your own little periodic table, sketch it, and then quickly write up electron configuration for the first, say, 5 or 6 or 7 or 10 different elements. And you might find a bit of a trend. And that's why we call these things S block and P block.
All right.
Abram.
Another question on top of those. How do we use the configuration to find the element number?
Okay. As you look at the electron configuration, and I had quite a few of them up here, go and find the final filled energy levels. And that will tell you, okay, it's in the 3rd energy level, so you can go 3rd period, and how many valence electrons does it have, and then how you would count across to the groups. Okay, so hopefully that will help you.
All right, last one for now. Is there a relationship between atomic radius and atomic number?
Well, that was the challenge question that I raised. Yes, there is, but be careful. As you go along the period, the atomic number increases, but atomic radius decreases, gets smaller. As you go down a group, the atomic number increases and the atomic radius also increases. So go back to that challenge question, because that's the answer for the challenge question.
Awesome, Tracy. Thank you so much for the great show.
Excellent. Thanks so much, Abram. Thanks, Mindsetters. Keep thinking, keep working, keep well, and God bless.
Thank you so much. Keep learning. That's the spirit. Otherwise, from me, AB, and Tracy, we just want to say thank you for your time. And till we meet some other time. Peace.